In the last lesson, you learned how to multiply and divide rational expressions. So we're going to move forward in this lesson with adding and subtracting rational expressions. Now, since a rational expression is in a fractional form, all of the skills that you learned to add and subtract fractions back probably in elementary school and middle school still apply. And so if you recall, if we can just do a simple scenario here. If I want to add these two fractions that have a different denominator, we need to get the least common denominator, or the least common multiple for the denominator. So you've heard it probably called an LCM and sometimes an LCD, so either one of them is fine. Now, what you want to do here is find the value that they have in common, the least value that they have in common. And so really what's going on here from a least common multiple standpoint is if you just start doing multiples of each one of these, you got 2, 4, 6, 8, and on and on. And then you have 3, 6, 9, and on and on and on. You can see that the least common multiple between these two is 6. And so if we want to get both of them to have a denominator of 6, we would have to figure out what do I need to multiply times each of them to get the 6. So 3 times 2, and again, if I do something to the denominator, I also have to do that to the numerator, and as well on the other fraction. And so now you have a situation where we have a common denominator, and we can add the numerators. And so that's just a quick refresher from your probably late elementary school mathematics course. Now, that is going to apply to the rational expressions as well, except now instead of dealing with numerical values for least common multiple, we're going to deal with polynomial expressions. And so you can see here in this bolded area, it says to find the LCM, factor the expression completely, and then find the product of the prime factors. And so we would want to then take each individual part, the greatest of those, and that would be our least common multiple. So if you like, go ahead and try sample problem number 1, parts A and B, and then you can come back and look at the solutions. We'll start here with a simple factoring of each one of these. So that gives me for 2x plus 4, and then the other factors. Okay, and so for our common multiples, since there's nothing exactly the same between these two, we have to use everything as a common multiple. And so basically our answer would be all of these factors together would represent our least common multiple. So let's take a look at the next one. So we have 3 separate polynomials here that we're going to try to find the least common multiple for. So again, factor each one of them individually. And so what you see here is we have each of these factored, and so we need to take the greatest power of each one of these as our least common multiple. Now notice there are some commonalities here. So first and foremost, I have x minus 1. That's not given to me anywhere else in the multiples. But I do have x plus 4 here and here. I do not need to count that twice. Counting it once is good enough. And then you notice that we have x minus 2. And so here we have it twice, so our greatest power of x minus 2 is x minus 2 squared. So we actually have to count both of those from our prime factorization, and that's ultimately what you did here with some prime factorization. So that would be x minus 2 squared, and that would be our least common multiple between these polynomial functions. Now, understanding this process of finding the least common multiple between polynomials is extremely important, because that's what you're going to be doing whenever you're dealing with the rational expressions and the denominators are polynomial functions. So make sure that you really understand this well before we move forward into the actual adding and subtracting part. Now we use this idea of the least common multiple of a polynomial expression in the form of a denominator. So now we move into LCDs in rational expressions. And so you can see here in example number 1 that we have a situation where we're adding 2 rational expressions to each other. And we really need to get a common denominator so that we can add the numerators together and then put that final value in simplest form. It also asks us to state any excluded values or restrictions on the variable. You remember that that's just simply any value that will make any of the expressions undefinable. So if we look at this, the first thing that we did in this first step is we actually factored the second expression, and we can see that we have a common x minus 1, but the first expression doesn't have an x minus 2, so that needs to be applied as a common denominator to the first expression. And you can see in the second step in red where we did that to both the top and the bottom, very similar to what we did when we were adding 1/2 plus 1/3. So once this is done and there's a common denominator between the two rational expressions, we can actually combine those under one denominator and then proceed from there to simplify the expression as far as we can. Now, if you look at the final answer, x plus 1 over x minus 2, we see that x cannot equal to 1 as an excluded value. Now, that may kind of not make sense right off the bat, but if you look back to the original problem, you can see we had x minus 1 and x minus 2 in the denominators between the two rational expressions. And so we have an excluded value of x cannot equal to 1 and x cannot equal to 2, because in the original rational expressions it would make those undefined, and you can't add undefined fractions to each other. So you're not just looking at the simplified final answer, you're also looking at the denominators of the original expressions. Okay, so what I'd like you to do is go ahead and give sample problem number 2 a try, come back, take a look at the solution, and then from there you can move on to sample problem number 3 if you feel like you're understanding very well, and then watch the solutions on that as also. Okay, first thing I'm going to do is factor here, and we can see very clearly that x minus 1 is the same, but we have an extra multiple of x that needs to be applied to the first expression. So I'm going to multiply x to both the numerator and the denominator, and I'm going to go ahead and work out that particular operation. Now you can see that we have a common denominator, and so I can the expressions in the numerators and put it all under one common denominator. Once I do that, it's probably a wise thing for me to just go ahead and factor the numerator in full and then simplify, leaving me with x plus 2 over x is my simplified answer. Now, let's keep in mind here that I have to go back to the original parts to get my restricted domain, and so we'd see that x cannot equal to 1 or 0. Okay, so that's a simplified version of adding two rational expressions. Felt good about that. Go ahead and try sample problem number 3. So as we start sample problem 3, you can see I've quickly factored the denominators, and we have 3 separate parts. We have an x, we have a 2, and we have an x minus 2. Now the x minus 2 is common in both, so there's really no adjustment that needs to be made there in those denominators. But we need to multiply 2 to both the numerator and denominator on the first expression, and we need to multiply x to both on the second expression. And so I'll go ahead and do that now. You can see from this result, now that I've applied the least common denominator to both rational expressions, I've come up with a subtraction problem that has the same denominator. Now, keep in mind, since this is subtraction, when I combine these together under one denominator, that negative actually has to be applied to the whole expression in the second part. So I'll go ahead and do that now. Okay, now we've gotten this to a place where we can start to eliminate and simplify parts a little bit, and so I'll just go ahead and move forward from here. You can see that the two x's are going to cancel each other out on the numerator, so they don't cancel out with the denominator, however, because the operations on top just eliminate them. So we're going to be left with negative x squared plus 4 over 2x times x minus 2. Okay, from here we're going to actually take out a negative 1. We're going to factor out a negative 1. And then we can see that this leaves an x squared minus 4, which gives us a simple difference of squares problem. And now we're left with x minus 2's that can eliminate each other. And I'm going to distribute the -1 back across there for my final simplification, leaving me with the following expression. Now, we need to state our excluded values. Clearly, x cannot equal 0 here. But if you go back up to the original rational expressions, we had x minus 2 in the denominator. So x can also not equal 2. So our restricted values are 0 and 2 in this case.